Hello friends, I welcome you in lecture number 2 on functions. In this lecture we will define one-to-one functions or injective function. So first we understand the definition of one-to-one function with the help of example. Suppose I consider a function from one set to another set. Suppose this set is denoted by capital A, this set is denoted by capital B. And here I consider these four natural numbers. Here I consider these elements. And suppose image of this 1 is B, image of 2 is A, image of 3 is C, and image of 4 is E. So we consider a function f from finite set A to another finite set B such that f of 1 is B, f of 2 is A, f of 3 is C, and f of 4 is E. So here we can observe that these 1 and 2 are distinct elements and their images are also distinct. Here we assume that these A, B, C, D, E all are distinct elements of set B. So we can note this thing: 1 and 2 are distinct elements and their image is f of 1, which is B, and f of 2 are also distinct. Similarly, if we consider this possibility 1 and 3, then we can see image of 1 is B, image of 3 is C. So we can say that image of 1 and 3 are also distinct. So we can see that there are no two elements which are distinct and having the same image. If we consider any two distinct elements of set A, then their images are distinct. That we can write in this way. Suppose I consider any two elements in set A, and if I take x and y as distinct elements, then we have this type of situation. Images of x and y are distinct. If this happens for every pair of elements in the domain of function f, then we can say that function f is one-to-one. So one-to-one function means function is one-to-one if distinct elements of the domain has distinct images. That means if x and y are different, implies fx and fy are also different or distinct for all possible values of xy in the domain of f, then we say that function f is one-to-one or injective. So that definition I have written here. A function f from A to B is said to be one-to-one or injective or simply one-one if distinct elements of A is the domain of function, are mapped into distinct elements of B. In other words, we can write this statement, same statement we can write in this way also. F is one-to-one if x1 is not equal to x2, implies f of x1 is not equal to f of x2 for all x1 x2 belongs to A, which is the domain of given function f. Now the same statement we can rewrite in another way also. This statement says that distinct elements have distinct images. So this we can rewrite in this way also. We can write that if two elements x1 and x2 are having same images, then x1 and x2 cannot be distinct. F of x1 equal to f of x2 must implies x1 and x2 are equal. So we can use this one or this one to prove that function is one-to-one or injective or onto. So we will remember both the equivalent definitions. X1 is not equal to x2 implies f of x1 is not equal to f of x2 for all possible values of x1 x2 in the domain of f. If this happens, then function is one-to-one or injective. And equivalently, we can use this one also. If f of x1 and f of x2 are equal, then we must have x1 and x2 equal, and this must happen for all values of x1 and x2 in the domain of f. So both the statements say that distinct elements must have distinct images. This statement means distinct elements in the domain of a function must have distinct images, and this statement is equivalent to that statement which says that suppose two images are equal, then these x1 and x2 cannot be different. F of x1 equal to f of x2 must implies x1 equal to x2 for all x1 x2 belongs to domain of f if f is 1 to 1. We consider one example. Determine whether the function f from set ABCD, we denote this set by capital A. Suppose A equal to ABCD 2 1 2 3 4 5, and set B is 1 2 3 4 5, and it is given that image of A is 4, image of B is 5, image of C is 1, and image of D is 3, and we have to check whether this function from A to B given by this is 1 to 1 or not. So best way is we consider this Venn diagrams for sets A and B, and we observe that whether distinct elements have distinct images or not. So here I consider ABCD, and in set B I have 1 2 3 4 and 5. Image of A is 4, so I join A with 4. Image of A is 4, image of B is 5, image of C is 1, and image of D is 3. So we can see distinct elements of set A are having distinct images in the set B. Therefore this function is 1 to 1. So we can write that since distinct elements of set A, which is nothing but domain of F, have distinct images in set B, we can say that F is 1 to 1 or injective. So if we have finite set, we can check in this way. We can use the Venn diagrams and we can observe that whether distinct elements are having distinct images or not, and we find that this function is 1 to 1 because distinct elements in the domain has distinct images in the codomain. This condition is satisfied if we take any two elements x1 x2 in set A which are distinct, then we observe that their images are also distinct, and this is true for all x1 x2 which can take these values A, B, C, D from set A. Therefore this function is 1 to 1. We consider another example. Here our function is x square and its domain is this set of integers, and codomain is also set of integers. Our function is function from set of integers to set of integers, and it is given by fx equal to x square, given that f is a function from z to z and defined as fx equal to x square, and we have to determine whether this function is 1 to 1 or not. So we can think that whether if we take any two elements from the domain, then their images will be distinct or not. If I take any two integers x, y in the domain, then whether this is possible or not. If x and y are different, then fx and fy are different or not. So how to check this condition will be satisfied or not? Or we can check in this way also, fx equal to fy. If fx and fy are equal, then x must be equal to y. So we can use either this one or this one, and we can check whether this is satisfied or not. So first we try to prove that condition. We try to prove that if fx and fy are equal, then whether x and y are equal or not. So suppose for xy belongs to z, which is the domain, fx and fy are equal, then we check that what this will give us. So fx is x square and fy is y square. So we have x square equal to y square. Now this implies x equal to plus or minus y. So now we obtain that if x square equal to y square, then there are two possibilities, either x equal to y or x equal to minus y. So it is not guaranteed that we will obtain only x equal to y. So from this we can have the idea that there are chances that this function cannot be one-to-one, because we are not strictly getting that x equal to y. If fx equal to fy, then we find that x equal to plus or minus y. That means x can take the value y or x can take the value minus y. So it is not, we are not having from this that f can be one-to-one. So now what we can do is, first we are trying to prove that function is one-to-one or not, and we are having doubt that function may not be one-to-one. So now if function is not one-to-one, then we must have at least one pair of x and y such that x is not equal to y implies fx equal to f of y. If function is one-to-one, then this condition must be satisfied for all possible values of x and y. So if we want to disprove that function is one-to-one, we have to find out one pair of x and y. We have to show the existence of x and y such that x is not equal to y but fx equal to fy. Fx is x square and fy is y square. So we have to find out particular values of x and y such that x and y are different but their squares are equal, and that is easy to find out. If we take x equal to say 2 and y equal to minus 2, then x and y are different, but if we take square of x and square of y, we will obtain 4. So for these two values x and y which are in the domain of this function, we observe that x and y are distinct but their squares or their images are not distinct. Therefore function is not one-to-one. So if we want to prove that given function is not one-to-one, we have to give counter example. We have to find out two possible values of x and y which are distinct but their images are equal. So now here we should write in this way: for x equal to 2, y equal to minus 2 in the domain is z, we observe that x and y are different but x square equal to 4 and which is equal to y square. Therefore fx which is equal to x square and fy which is equal to y square, but fx and fy are equal. Okay, so thus what we have obtained, x is not equal to y but fx and fy are equal, and if our function is one-to-one, distinct elements must have distinct images, and here we have obtained two distinct elements whose images are equal. Therefore f is not one-to-one, or f is not injective or one-one. These are different words, you should remember. Injective is another word for one-to-one function, or we can simply write f is not one-one. So in this way we can decide whether given function is one-to-one or not. If function is one-to-one, then we have to prove this condition: x is not equal to y implies fx is not equal to fy for all x y belongs to domain of f. Or we have to prove this condition: fx equal to fy implies x equal to y for all x y belongs to domain of f. But if function is not one-to-one, we have to find out two distinct elements x and y for which fx and fy are equal, which we have found here. X and y are different, but fx and fy are equal. Therefore this function is not one-to-one. Now we consider this example. Determine whether the function f from R to R defined as fx equal to x plus 1 is one-to-one or not. Here they have used this word injective. Fx is equal to x plus 1 and its domain is set of real numbers. So now here we can prove using this one or this one. We have two equivalent conditions. Either we can use this condition or this condition to prove that this function is one-to-one. Suppose we consider that for two elements, let x, y in the domain of f, which is set of real numbers, let x, y belongs to R, be such that their images are equal. We are considering arbitrary elements in the domain of function such that images are equal. Now if function is one-to-one, then x and y must be equal. If function is one-to-one, then we have to show that fx equal to fy implies x equal to y. Now fx is given by x plus 1, so here we write x plus 1 equal to fy will be equal to y plus 1, and we can see 1 will cancel out and we will obtain x equal to y. So we take arbitrary elements in the domain of given function such that their images are equal, and we show that x equal to y. Therefore given function is injective or one-to-one. And if we wish, we can use that equivalent condition also. Instead of proving in this way, we can prove using that equivalent condition also. Let x, y belongs to R in the domain of f such that x and y are distinct, such that x is not equal to y. And we have to show that if x and y are distinct, fx and fy are distinct. So we have to show that fx is not equal to fy. We have to prove this one. If x is not equal to y, we have to show that fx and fy are not equal. Fx is x plus 1, fy is y plus 1. Now here x and y are different, so if we add 1 on both the sides, then also we have this inequality. Now this x plus 1 is nothing but fx and y plus 1 is nothing but fy. So we have taken two arbitrary elements x and y in the domain of f such that these elements are distinct, and we proved that their images are also distinct. Therefore f is injective. Okay, so it is very easy to prove that given function is one-to-one. We have to just remember these two conditions. if x is not equal to y implies fx is not equal to fy for all possible values of x and y in the domain of f, then function is 1 to 1. Or we can prove in this way: fx equal to fy implies x equal to y for all possible values of x and y in the domain of f, then also f is 1 to 1 or 1 1 or injective. So remember this definition. Sometimes they can ask you to check whether given function is 1 to 1 or injective or 1 1. So this is all about this session. I hope you like it. Thank you.